In this video, we work another curve sketching problem. This was a function that I saw in one of our integration videos where we were computing a definite integral of 3 raised to the cosine of x times sine of x. Thought it was a really neat curve. Lots of interesting things happening. We have minima and maxima on the interval from 0 to 2 pi. We've got some points of inflection. I just thought it would be an interesting one to talk about as far as intervals where the function's increasing and decreasing and where the graph is concave upward and concave downward. And the derivatives are relatively easy to compute. So I thought it would be a good opportunity to practice that derivative of a to the x. So this is our function. We can see just from looking at it that it's periodic. The function itself is 3 raised to the cosine of x times sine of x, and we know cosine and sine are periodic with period 2 pi, so this function is periodic with a period of 2 pi. So that's 0, that's 2 pi, that's 3 pi, that's 4 pi. So if we understand what the graph looks like on the interval from 0 to 2 pi, then we understand the whole thing. So we'll primarily focus on that interval from 0 to 2 pi, and then use that to generalize what happens for the entire curve. So here, this is what we're looking at. Here's our curve. Now, in order to, and of course, the domain is all real numbers because you can put in any x value to sine cosine functions and you get a real number out. So we'll compute the first derivative. Now, this is the simplified version. When I computed the first derivative, I just said f prime, and I'll just say PR for right now, of x equals, and then I used the product rule. I've got 3 cosine of x times sine of x. So we'll have the derivative of the first, which is natural log of the base, times the same exponential, 3 raised to the cosine of x, times the derivative of the inside, which is negative sine of x. That's derivative of the first times the second. So I'm going to multiply by another sine of x. So that's going to give me a negative sine squared x. So that's the derivative of the first times the second. And then we add the derivative of the second times the first. Derivative of sine is cosine. And then we'll multiply by that 3 raised to the cosine of x. Whoops. It traded that 3 like a subscript. Sorry about that. We got cosine of x times 3 raised to the cosine of x. And so that's our derivative graph. And if you factor out that 3 cosine of x, what you end up with is if negative 3 times sine squared x plus cosine of x times that 3 raised to the cosine of x. Now 3 raised to the cosine of x, excuse me, is always a number between 1/3 and 3 because cosine is always between -1 and 1. So we don't get any zeros from that exponential factor. But we might get zeros from this sine squared factor, or this this polynomial in sine squared and cosine. But the way I want to think about it is I would like to think of this as a polynomial in cosine. So what I do is I replace my sine squared with 1 minus cosine squared. If I replace that with 1 minus cosine squared x, because sine squared plus cosine squared is 1, and then I distribute this negative natural log of 3 to all of the terms. I have negative natural log of 3 times 1. That's my constant term. Then I've got a positive natural log of 3 times cosine squared as my sort of ax squared term. And then my middle term is just that constant times cosine of x. Now this expression in parentheses is quadratic in form. It's not a quadratic function, but it's quadratic in the sense that if u equals cosine of x, we end up with a constant times u squared plus u plus a constant. So if we can find the roots of that quadratic form, then we can find the values of x that cause that function to be 0. So that's kind of the plan. Now, one other thing that I did after I graphed this, or after I computed the derivative using the product rule, made a substitution, sine squared equals 1 minus cosine squared, and then rewrote it as this expression, this exponential type function times something that is quadratic in form, was I said, let's have Desmos graph that derivative. So we graph f prime, and you see that their f prime and my f prime are the same. So their f prime is the green curve, my f prime is that orange curve. So we're getting the same function either way. But I want to make sure that my students know how to do that computation. So we know how to do the computation just using the product rule and then using a trig identity to simplify. And then we say, okay, well, when is this function 0? Because we're looking, whenever you have f prime, we want to know where it's 0 so that we can figure out where the function is increasing, the original function is increasing and decreasing, where the original function has a relative extrema. And then we can also look at the relative extrema of f prime to determine the zeros of f double prime. So when I'm looking at this, I'm going to hide the graph of f and just focus on that graph of f prime. This is what we've got on the interval from 0 to 2 pi, and we're interested in the zeros of this function. You'd say, okay, how do I find the zeros? Well, you'd set the 3 to the cosine of x equal to 0, which is never 0, so you don't have to worry about that. And then you've got this polynomial expression, or this function that is quadratic in form. And you want that to be equal to 0. Now, if u is equal to cosine of x, this is natural log of 3u squared plus u minus natural log of 3. Then the two roots of that are u1 and u2, and those are just given by the quadratic formula. Negative b plus or minus the square root of b squared minus 4ac, all divided by 2a. So this is our first root for u, and this is our second root for u. But again, those are not the x values that cause this to be 0. The x values that cause this to be 0 are given by the arc cosine of these u values. And that cosine function, the original cosine function, is periodic. And arc cosine has some restrictions on it. Arc cosine is only going to give us an angle between 0 and pi, and we actually want all of the angles that give us that corresponding u value. We're actually solving the equation u equals cosine of x, and that u equals cosine of x is equal to this particular value. So for my u1, I've got u1 equals this 0.644 approximately. And so what that is telling us is that I want the x values that give me a cosine value of 0.644. And there are infinitely many of them, infinitely many possibilities. Now, that cosine value is positive, and that 0.64, it's going to be positive in quadrants 1 and 4. Now, when you use the arc cosine function, it's only going to give you that angle in quadrant 1. So you have to subtract that reference angle from 2 pi to get the angle in quadrant 4. Now for u2, we have u2 equals this negative 1.55. Well, cosine of x is never equal to negative 1.55 because we know cosine is always between negative 1 and 1. We're never going to get a negative 1.55 out of a cosine function. So that u value does not correspond to any values of x. Although if it was in the range from negative 1 to 1, we would actually have potentially 4 values of x that cause that equation to be 0 on the interval from 0 to 2 pi. Then we would add 2 pi as many times as we want to each of those numbers to get all of the possible solutions to that equation, f prime equals 0. So I say, okay, well, what's my first one? Well, I said, let's take the arc cosine of this number. I think I used u2, and it said, shows that it's undefined, which we can see. And then I said, okay, the other two solutions come from taking the arc cosine of u1 and then 2 pi minus the arc cosine of u1. So the arc cosine of u1 is this 0.87, which is this root right here. And then the arc cosine and 2 pi minus the arc cosine of u1 is that value right there. And so that's what we get. So those are the zeros of the first derivative. And when we evaluate the first derivative at those x values, we don't get 0. We get this very, very tiny number, negative 4.5 times 10 to the negative 16th, and negative 1.35 times 10 to the negative 15th. That 10 to the negative 16th and 10 to the negative 15th are so small, they might as well be 0. So we can graph plot that point, x1, and then f prime at x1. That should be a 0. And it is 0 according to Desmos when it's rounding on the graph. And then we'll also find the corresponding f value at, or the value of the function at x1. Now, the first derivative is going from positive to 0 to negative at that point. So the original function should be going from increasing to having a 0 slope to decreasing. So we should have a relative maximum at that location. And then at x2, that's that 2 pi minus the arc cosine of u1. We're over here. Now the first derivative goes from negative to 0 to positive. So the original function is going to go from decreasing to having a 0 slope to increasing. And if we evaluate the function there, we get that y value on the function. So this should be a relative min because it's going to go from decreasing to having a 0 slope to increasing at that location. Say, okay, so those are the only zeros of f prime on the interval from 0 to 2 pi. So those are our only relative extrema on the interval from 0 to 2 pi. Now the other relative extrema come from adding 2 pi or subtracting 2 pi from these x values as many times as we like. Now the relative extrema of f prime actually correspond to points of inflection of our original function. I want to make sure I have enough juice in my battery. I've got 10% left, so I'm good to go. But we can see 1, 2, 3, 4, 5 relative extrema of f prime. Now, those are going to correspond to zeros of the second derivative. So if we want to, we can compute the second derivative. You can also see some of the values. You can see that we've got a maximum at 0, a maximum at pi, a maximum at 2 pi, and then there are a couple of values in between, and it's not as easy to read those, where we've got 2 relative minima. And those are going to correspond to points where the second derivative changes sign. So, or x values where the second derivative changes sign. So those are going to be our points of inflection. Now to find those, we can compute f double prime and then use the factored form of f double prime to find the values of, or the x values that correspond to a 0 second derivative. And at those x values, our first derivative will have relative extrema. So let's look at our original function f, or excuse me, f prime. I want to take the derivative of that with respect to x. I've already done the calculation, but I want to do it again with you guys. So here's my f double, or my f prime, and I'm just going to say f double. I'm taking the derivative of this with respect to x. I'm just going to type that and hide it. Okay, so we're trying to take the derivative with respect to x. Well, according to the product rule, we'll have the derivative of the first, which is natural log of the base, times 3 to the cosine of x power, times the derivative of the inside by the chain rule, so that's negative sine of x. That's derivative of the first times the second. So I'm just going to copy and paste that. Plus the derivative of the second. Now the derivative of the second requires the chain rule as well. So we're going to have, from this piece, the natural log of 3 is just a constant. And the derivative of cosine squared is 2 times cosine of x by the chain rule. So the derivative of function squared is 2 times the function times the derivative of the inside. So we've got a negative sine of x there. And then the derivative of cosine of x is, of course, negative sine of x. And the derivative of natural log of 3 is not 1/3. It's just 0 because natural log of 3 is just a constant, right? So that's the derivative of the second, and then we'll multiply by the first. And then, so you've got this form, and it's got a lot of terms. But one thing that I noticed is that this is sort of one big term, and then this is sort of one big term, because this is what we get from the product rule, derivative of the first times the second, and we're adding derivative of the second times the first. So when I look at this expression and this expression, and I say to myself, what do they have in common? Well, they've got that 3 raised to the cosine of x in common. So I factor that out from here, and that comes out front. And then I also look at this natural log of 3 times negative sine of x times this sort of polynomial form involving the cosine of x. And then on this one, I've got a term involving a negative sine of x and a negative sine of x. So since they both have a negative sine of x in common, this one has a negative sine of x as a factor, and this one has a negative sine of x as a factor, I can factor out that sine of x term. It looks like I didn't factor out the negative, even though I think if I had done it this way, I would have. I factored out just the sine of x. Then I said, okay, if I factor out the sine of x and the cosine of x, what am I left with? I've got this negative natural log of 3 times this expression. So that would be negative natural log of 3 quantity squared times cosine squared x. And then I'm subtracting negative natural log of 3 times cosine. And then I'm adding natural log of 3 squared because I'm distributing in a negative natural log of 3. And then here I factored out a sine of x. So I'm going to have a negative here and a negative 1 there. And all of this is multiplied by that 3 cosine of x, or 3 raised to the cosine of x times the sine of x. You say, okay, where are my like terms? I've got negative 3, or negative natural log of 3 squared times cosine squared x. And then I've got negative natural log of 3 cosine of x. And then I've got 2 more of those. So I've actually got negative 3 of those if I collect like terms. And then I've got this natural log of 3 squared minus 1. So if I factor, or if I simplify that, then I get this form down here, which is what I've already computed. So I've got my negative natural log of 3 squared times cosine squared minus 3 natural log of 3 times cosine plus the constant term, which is the natural log of 3 squared minus 1. So I know this looks complicated, but this is really just like ax squared plus bx plus c, where these coefficients involving the logarithm are just constants. And then instead of an x, we've got a cosine squared x and a cosine of x, and then just a 1. So you've got f double prime is equal to that. If we look at that graph, it's very complicated. It's kind of cool looking, actually. I like it. Let's see. Trying to get rid of my f prime, though. So just so we can focus on that second derivative. And I still got some points plotted from before. So relative extrema of f, values of f prime as well. So I'm going to get rid of those real quick. Excuse me. But that's my f double prime. And then if I have Desmos graph f double prime, we see it's the same thing. So my graph and Desmos graph are the same. So that's good. We say, okay, well, when is f double prime equal to 0? Well, it's equal to 0 when the exponential term is 0, which is never 0. It's always between 1/3 and 3. And then when sine is 0, on the interval from 0 to 2 pi, that's going to happen at 0, pi, and 2 pi. We know sine is 0 at all the multiples of pi. And this expression, again, is quadratic in form. So I'm going to solve it using the quadratic formula. And if those roots are between -1 and 1, we'll take the arc cosine to get a corresponding x value. That'll give us one of the x values that correspond to that root. Now, because cosine is positive in 2 quadrants rather than, or positive in 2 quadrants and negative in 2 other quadrants, and that arc cosine function is only giving us one of them, we'll have to use a reference angle to find the other x value that corresponds to that particular cosine value on the interval from 0 to 2 pi. And then remember that the function is periodic, so it repeats itself. So that's what we've got. So we said f double prime is 0 or at 0 and pi and 2 pi. And then we also said that f double prime is 0 at those two, or when that quadratic form is 0. Now to find the roots of the quadratic form, I said, let's let u equal cosine of x, and then u is equal to -b plus or minus the square root of b squared minus 4ac, all divided by 2a. A, b, and c are kind of complicated this time, so when I simplify them, we end up with all these logarithms everywhere. Don't worry about that. They're just numbers, right? Desmos has no problem with computing a natural log of 3. So you just type all of that in. And this is the -b plus the square root of b squared minus 4ac all divided by 2a. When I evaluate that, I get a U value that's negative 2.79. Arc cosine or cosine of x is never negative 2.79. So there are no x values that correspond to that particular value of U. If I try to evaluate the arc cosine of that U value, I get an x value that is undefined. But at the other one, when U is equal to negative b minus the square root of b squared minus 4ac over 2a, we get a U value that's 0.06. So the cosine value is 0.06 sometimes. Cosine values are between -1 and 1. And so there are actually going to be two x values on the interval from 0 to 2 pi when our cosine value is 0.06. So to find those, we take the arc cosine of U4, which gives us this 1.509 approximately. And then that's in quadrant 1. And that's what the arc cosine gives us. It always gives us an angle between 0 and pi. So it gives us an angle in quadrants 1 or 2. To get the angle that is also positive, that also corresponds to that positive cosine value. In quadrant 4, we have to use this arc cosine of U4 as our reference angle. So we're going to let x4 equal 2 pi minus that arc cosine, or x4 is 2 pi minus x3, which gives us that 4.77 number. So if I evaluate f double prime there, I should get a 0. And that's what we see on the interval from 0 to 2 pi. Okay, so now what I want you to look at, what I want you to focus on, and actually let's change the range, or not the range, the domain, essentially. We know the domain is all real numbers, but we just want to look at the part of the graph between negative pi over 6 and 13 pi over 6. So basically I'm focusing on 0 to 2 pi, but I want to add pi over 6 in either direction just to make it clear that the function actually repeats. So this is what we've got. And we see that the second derivative is negative between 0 and that 1.509 number. So since the second derivative is negative, the original function should be concave downward. And then the second derivative is positive from 1.0 or 1.509 to pi. So the original function should be concave upward. Then it's negative on the next interval from pi to that 2 pi minus the original reference angle, that 1.5, which gives us the 4.77. It's concave downward there because the second derivative is negative. Then the second derivative is positive from 2 pi minus that arc cosine of U4 to 2 pi. So the original function should be concave upward there because the second derivative is positive. Now, if we look at the original function now, sorry, I have to go back through a lot of code here. There it is. There's our function. Now I think I'd like to look at it on the interval with y values between negative 3.5 and 3.5. Okay. So the claim is that these zeros of the second derivative are where the original function changes concavity. So let's evaluate the original function at those points. So I want f at 0. I want f at pi. Not f prime at pi, I want f at pi. And then I want f at 2 pi. And then I want f at that arc cosine of U4, which we're calling x sub 3. And that 2 pi minus the arc cosine of U4. And so that's what we've got. And so if you zoom out a little bit, actually, if you hide f double prime, you can see it a little bit better. That's what we've got. It's concave downward, then concave upward, then concave downward, then concave upward. And we can see that. Now if we graph f double prime again, we can see that's consistent with the graph of f double prime. F double prime is negative when the original function is concave downward. F double prime is positive when the original function is concave upward. F double prime is negative when the original function is, or negative here where the original function is concave downward. And then f double prime is positive there where the original function is concave upward. So that's all consistent. Now we also have our original first derivative should have relative extrema at those points of inflection. So let's graph the first derivative now. Okay, so this is our graph. And I've got all those points graphed. Probably don't want to have all those zeros of the second derivative graphed right now. So I'm gonna get rid of those. But if we focus again on that interval from negative pi over 6 to 13 pi over 6, this is what our graph looks like. Our y values, want them to go from 3.5 to negative 3.5. Now, my claim is that the points of inflection, these white points on the original graph, correspond to relative extrema of the first derivative. So let's look at the relative extrema of the first derivative. I can see just from looking at this graph that we've got f prime has relative extrema at 0, pi, and 2 pi. Whoops. And that's a relative max, a relative max, and a relative max. And then at this 1.509, it looks like we've got a relative min. And then at 2 pi minus 1.509, I think that's that 4.77 number, we should have a relative min as well. I called those x values x sub 3 and x sub 4. Oops, that's not what I want. So we see we've got a relative minima there. And now we see, now if you look at where the function f prime is increasing or decreasing, you can see the relationship between that and the graph of f being concave upward or concave downward. So on the interval from 0 to this 1.509, we see that the f prime is decreasing. Well, when f prime is decreasing, the graph should be concave downward, the original function. And the original function is concave downward between 0 and 1.509. And then between 1.509 and pi, the f prime is increasing. So the original graph is concave upward. And then from pi to 4.77, the original, or f prime is decreasing. When f prime is decreasing, the original function should be concave downward, and it is. And then the derivative is increasing from 4.77 to 2 pi. And so that means the original function should be concave upward, and it is. So between the first derivative and the second derivative, we can find all of those points of inflection and how they relate to the original graph. The points of inflection of the original graph are the zeros of the second derivative and the x coordinates of relative extrema of the first derivative. I've got way too many points plotted here. But if you graph f double prime and f prime, you can see that relationship. And if we get rid of that graph of the original function, think I may, did I already do that? If we just graph f prime and f double prime, we've got our relative extrema of our first derivative graphed there. If we graph f double prime at the same time, we see that. We see where the original graph is concave, or we can see where the relationship between the first derivative and the second derivative. So where the first derivative is decreasing, the second derivative is negative. Where the first derivative is increasing, the second derivative is positive. First derivative is decreasing, second derivative is negative. First derivative increasing, second derivative is positive. And then the first derivative is sort of decreasing again, and the second derivative is negative, and it just repeats. It repeats that pattern over and over again. And then again, when the second derivative is negative, the original graph is concave upward, and the second derivative is positive, the original graph is concave downward. So I'm going to get rid of all these points now. But with this information, with the graph of f prime and f double prime, we know where the graph original function is increasing, we know where it's decreasing, we know where it should have points of inflection where it changes from concave upward to concave downward. And I think I want to graph just those points on the original function f. So what we're looking at right now is f prime. Try to get rid of f prime for a second and look at f, the original function. I just like these graphs. I think they're pretty. And the fact that they're periodic is cool too. So this is our function. And we want to graph that for x values between negative pi over 6 and 7 pi over 6, or not 7 pi, 13 pi over 6. So I'm just going from 0 to 2 pi. But I want to add, pi over 6 in either direction. So we know that it repeats. And now I'm going to plot the relative extrema and the points of inflection. So we know our relative extrema correspond to zeros of the first derivative. And so the first derivative is 0 at that x value. Oops, not that one, that's f prime. And that x value. And then points of inflection are when the second derivative is 0. Our second derivative is 0 at 0 and pi. Oops. And at 2 pi. And then also at these points in between here, we had to set a quadratic form equal to 0. There was only one root that corresponded to a cosine value that actually made sense, a cosine value between -1 and 1. And so that gave us 2x values. There's a point of inflection there, and 2 pi minus that x value is the second point of, or is the second x coordinate of a point of inflection. And that's our graph. And if we want to, we can look at the graph of the first derivative and see how the relative extrema correspond to zeros of the first derivative. We can see how, we can look at the second derivative and see how the points of inflection correspond to the zeros of the second derivative. And we can look at the sign of the first and second derivative on each of these intervals to see where the original function is increasing or decreasing. We can see just from looking at this that the original function is increasing from this x value over here, from this minimum, this negative 0.87, which is just, again, that cosine value. We said that we had the arc cosine of a particular angle that gave us a value of 0.87. That was the number of radians that we would have. Now, if we have the same reference angle, we could call that other angle 2 pi minus 0.87 to get that 4.77 number, this x value. Actually, that's I'm talking about the wrong quadratic form. I'm sorry. But basically, this x value and then this x value have the same, correspond to the same reference angle. This is giving us a cosine of a particular value in quadrant 1. This is giving us a cosine of a particular value in quadrant 4. Now, rather than using 2 pi minus that reference angle, you could just use 0 minus that reference angle and get this x value. So if we go from the negative of that x value to the positive of that x value, our function is increasing. And then our function is decreasing from that x value to 2 pi minus that x value. And then it just repeats like that. That's where we've got increasing and then decreasing. But there's a lot more interesting things happening with that second derivative being 0 at a number of values. So that's it. I hope that makes sense. I just like it because there's lots of points of inflection, got lots of relative extrema. First derivative looks kind of cool. Second derivative also looks kind of cool. I hope you like it. I think it's neat.